SNF, for easy, cost-efficient, and sustainable EOR solutions. In a world where the energy demand continues to climb, oil extraction must be done in an environmentally responsible way. For EOR operations, this means reducing CO2 emissions. When changing from water flood to polymer flood, the water production can be reduced from 9 barrels of water to 3 barrels of water per produced barrel of oil. SNF achieves this with modular plug-and-pump installations for quick and cost-effective unit implementation with many added benefits. Polymer flooding involves increasing the viscosity of injection water to enhance sweep efficiency and ultimate recovery of oil within a deposit. SNF assists clients through every step of the process, from assisting screening and reservoir studies, polymer logistics, to on-site storage, mixing, and injection. SNF designs, implements, and operates on-site facilities for the client. Polymer flooding has a higher added value than water flooding. Due to the greater sweep efficiency of polymer flooding, the overall recovery will be accelerated with significant water production reduction per barrel of oil. Using SNF system, clients' water cut went from 90% to 70%, which means 3 times less water production per extra produced barrel of oil, savings on lifting operation and production costs. These benefits also result in a reduction of up to 3 times in greenhouse gas emissions during the operations. SNF improves the efficiency of oil production processes. Because polymer flooding is easy to implement and more mature than other methods, development time will be significantly reduced.
Palestrante de hoje é da empresa, que patrocinador do bronze, é CNE. Aqui eles vão apresentar 2 pessoas, o senhor Jorge Monzón e o senhor Eduardo Onilles. Aqui o Jorge Monzón, ele é da Universidad Politécnica de Madrid, hizo una maestría en ingeniería de petróleo en la Universidad de IFP de Francia. Atualmente trabalha como engenheiro de reservatório na SNE, na parte de polímero, na implementação do campo de Latinoamérica. Ele, anteriormente, ele trabalhou como engenheiro de Halliburton em completação de ferramentas e trabalha em diversas missões a nível de Sudamérica. Ele também é engenheiro petroleiro 2 anos na empresa Lundin International e principalmente trabalha em operações do campo e supervisação do campo também. Por favor, Jorge, se pode começar a sua palestra?
Ok, muito obrigado. Aqui tá bom?
Onde você prefere mais?
Não, tá bom, aqui legal. Bom, primeiramente, I'm going to speak in English. I'm going to make my presentation in English. So, my Portuguese be done a little bit, so you can make the question in Portuguese. So, first, I would like to thank you the Unicamp University for giving us the opportunity to make this presentation. So, as Jose Maria said, I'm working in SNF as a petroleum engineer and more giving support to the project in South America. My colleague Eduardo, who is going to help me out with this presentation, he's also a petroleum engineer, and he's supporting the activities more in the engineering side, commissioning and operation of the equipment. So the idea here is to show you how mature field can make this revitalization of these mature assets through one typical enhanced recovery technique, that is polymer flooding. And I'm going to show two different scenarios, both in South America, in Argentina and in Suriname. So this is the agenda. So I'm going to start with the principles of polymer flooding, very easy, and then we are going to go to the different cases, which are different reservoirs, different strategies, different challenges, and finally we go with the conclusion. So SNF is a chemical company, so we provide chemicals to different industries. The main one is the water treatment industry, and here we are going to focus on the oil and gas industry, specifically in the EOR segment. So in the EOR segment, SNF provide three things which are essential for the success of the project. So the chemicals, so polymers, polyacrylamide polymers, which could be different standard ones for high temperature, high salinity, can be in different forms, powder or emulsion. Then we have the engineering side that are going to allow us to put this chemical into the surface. So for that, we have created some patent, like the polymer slicing unit, that allows you to dissolve the polymer in solution, and the containerized units that are a way to easily implement the technology in the field. So Eduardo will give you a little bit more details on that. And then the systems that is essential for the success of any project, specifically here in the UR. So we follow our clients from the startup, commissioning, training, and the system during the whole project. Here are the two cases that we are going to show you in Suriname, and Argentina. We have started with, we have accompanied the clients from the beginning to today. So the principle of polymer flooding. The idea is to inject viscous water. So with this, first of all, the risk is going to be limited, because if we have already injected water, there is not that much. So, and with this, we are going to have going to improve the super efficiency. You can here see in the photo how with the water flooding you have different heterogeneities. You can get a quick breakthrough through the permeability channel. In exchange with polymer flooding, we have a more continuous front that allows you a better recovery and acceleration of this recovery. So when we are polymer flooding can be applied in different scenarios, but the two more common are when the mobility ratio is not favorable. So, for example, it's with heavy oils. and when the reservoir is heterogeneous. Even if we have a good mobility radio, if you have high heterogeneity between the layers, we are going to have, for sure, a quick breakthrough in the hypermobility layers. So, which are the key parameters for a good polymer flooding design? So, if we have a difference, we are operator company, we have different reservoir where we can apply polymer flooding. This is a good way to make good ranking of this reservoir, taking into account these parameters. So the oil viscosity, normally we move from 0.1 centiwatt, 0.1 centiwatt, and 10 centiwatt. So let's say that the higher the oil viscosity, you will have higher possibilities that you have done a bad sweep, and therefore you will have higher saturation oil in place. We need to remind that polymer flooding, we're gonna just mobilize the oil that is mobile. I mean, we are not gonna relay interfacial tension, we are not gonna make as the surfactant, so the idea is just to mobilize the oil that has been bypassed. So therefore, in our reservoir, we have already reached the residual oil saturation. There is no interest to go through polymer flooding because you are not going to mobilize more oil unless you make polymer. So then we have two parameters which are important for the chemistry that is going to be used. Which kind of polymer is going to be used for this reservoir? So temperature, normally the maximum limit that we have right now is 140 degrees Celsius. More than that, our polymer is not going to be efficient. We're going to have reduced viscosity when it is injected in the reservoir. The polymer is not going to stand these high temperatures. The same for salinity, 250 grams per liter. More than that will be a limit for the technology. In exchange, lower temperatures and lower salinities will allow us to use cheaper chemistries and reduce the concentration to reach our target viscosity. So that will mean that the OpEx that we're going to use for the project implementation will be much lower. Then we have another factor. As explained before, is the heterogeneity. It can be measured as extra parson value. So this heterogeneity can be controlled by the viscosity that's going to be implemented. So we have high heterogeneity. Normally, we are going to try to use a higher viscosity to control this problem and create a more homogeneous front. Then we have the spacing and thickness. So we consider that to start having some results in polymer injection, you need to inject at least 30% of more volume of your pattern. So if your spacing and your thickness is higher, therefore you will need to get much more polymer. So that means much more OpEx before having some results. So if I'm working in an operator company, I have my boss who's saying, hey, it makes 2 years and there is no result. Usually it's working. So it's hard to explain. So that is good to know when you are going to start the technology to go through a pilot that have lower spacing and lower thickness just to have better results and be able to show that the technology is working. So as I have said, the spacing and thickness, we are going to have an impact in the time that you will need to have a response of the pilot. Eduardo, I'll let you go through the typical scenario of chemical you are operating.
Yeah. Good morning. So that is very important that after all the simulation and all the lab guy have selected the polymers, we move into the workflow. No? That's very important to know how it's working, this pilot, the life of one project. We start with an injectivity test. It's normal that the time is 1 or 2 months. And the authenticity test is to try to validate parameters. Which parameters? Flow and pressure. The idea is to start with 1 well, 2 wells, maximum 3 wells. And the idea is to check is the critical parameter, the polymer selection is the good one. So we start with a step-by-step and compound with a low flow, low concentration, and after we see what's going in response of the wellhead, injector wellhead, and see what's going on with this pilot. Okay. For this pilot, we use little units, 2 containers, with 2 containers with different equipment, special equipment, compact, in order to move inside very quickly to site, look and pump. Yes. One commission is maybe 20 days, and we can start very fast. After that, we finish this injection activity, and the well is working good, we have good response to the well, we move into a pilot phase. Yes. And with this pilot phase, normally it's more than 4 wells, 5 wells. Yes. And we can have more like 6 or 36 months of time for this. We need to evaluate this one, and we need to evaluate the dilution and injection equipment. That is okay for the well. Okay. And this also we use it, installation is that we can use the same unities, but this one is big one. But with more silos, more capacity in injection, and and maybe one special equipment. After that, we move into one special case, special moment. So expansions of it. So we can normally it's 25 or 25 years. And this one, our critical parameter is to logistic polymer supply, storage, and use. Is our critical parameter. In this one, we use we try to perform a lot of improvement in injection pumps, okay, and about also what about about the silo or the logistic, about the polymer supply. Okay? So we have this. We have, you see that we start in the first months, and you can go to 25 years in one project polymer. Okay? So what is the standard polymer powder? Okay, we have the special equipment. We have a storage silo going to storage the polymer powder. Okay, we have a mixing equipment that use the water process and mixing with the polymer powder. We have a special equipment with the polymer side unit PSU. We can go to 1 to 1,000 ppm to 2,000 ppm of more solution concentration. Why we use this equipment? Because we can reduce the capacity of the equipment. It's normally we can use also an eductor. You know, eventually we have powder, we have water, we can mix it. But with this kind of equipment, this eductor, the equipment will be massive. You know, we use more time to dilute the polymer solution, to maturate the polymer solution, water solution, and your equipment will be bigger. So with this equipment, with this PSU, this is our technology, a special technology, we can reduce this size of the equipment. Okay? So if you use, the equipment is no bigger, you reduce your power, you reduce your OPEX, you reduce your CAPEX. So that is good also for the operation. After that, we have a maturation tank in order to maturate dissolve all the polymer. We need to have 30 to 45 minutes of homogenization. We have some agitator, and we have one metering pump that is providing the good pressure to the high pressure pump in order to push that in the reservoir. We're mixing with water, and we have an static mixer here in order to mix the model solution and the water. That is very important, and that we have in all our system in nitrogen blanketing. We know that polymer with the water coming with some component like iron +2, and coming with H2S. So if we have some oxygen with these 2 components, we can we can observe chemical degradation. So we're injecting nitrogen in our system in order to avoid oxygen in the equipment. So this is the standard for the polymer fluid. We have storage, mixing, maturation, and pumping, and nitrogen system in order to avoid oxygen.
Just one comment, Eduardo. Something that you need to know is here, what we try to do is first, we're going to create what, as Eduardo said, a model solution. So we're going to make a very high concentrated polymer solution. So we are talking from 1 to 2%, 20,000 ppm or 10 to 20,000 ppm. And then with another water inlet, here, we are going to dilute it to the target viscosity that the customer is looking for. And to give you an idea why in the pilot or the massification, the logistics is a very critical parameter. You can imagine in a standard pilot, we are consuming like 1 ton, 2 tons per day. When we go through the massification stage, we are around 20, 25 tons per day. So you need to be sure that you need at least 2 more for running your operation, and you need to have a storage of 25 tons per day. So this is very critical parameter. Go ahead, Eduardo, thank you.
So what about the principle of injection? So we have, we need to know on site is we have the water process available. If we have maybe on site, we have high pressure system because we inject in water fluid. We have in one injection, or maybe we have not this network on site. What's going on is we have no available injection pressure. We have the option to take the low pressure water and mix it, and with several pumps we can inject in one pump. We can inject in each way. No? This is one option. What happens if we have we have no water, high pressure system? We can use the low pressure system. We can mix it. We can use this water to prepare the model solution humidity, and we can mix it in order to have the good viscosity in the well. But what's going on if we have only one pump? So we can use several devices in order to this pump to go into the different wells. Okay, we can talk after about that. What about this? We have network on site. We have the water pressure network on site. So we can use this water high pressure, and we can dilute that. What is the differential between this one and this one is the size of the equipment. Is we have for this one, maybe we have, for example, we have 30 meters cubed. I don't know, it's 3,000 barrels per day. Yes, with a low pressure system. But I have this system. We can reduce the capacity of this equipment and use this network in order to inject in the well. So we can reduce the footprint in our system. So it's very important to determine and to see and observe on site, and it's very important for a pilot to know if we have availability from of the water injection pressure. So the question is how we can move into pilot phase. Fulfill. Yes, this is important because we can start with that. As in the beginning I said, we can start with a pilot with only one well, 2 wells, and how I can move into a fulfill. Like I start for 4 wells, how I can move into 100 wells, okay, 120 wells. And this is the case that we're talking about for Argentina project and Suriname project. We're moving from the one pilot phase that is 4 wells, 100 wells. So how it could move. So it's very important to know is we have existing infrastructure, that the water injection network. It's very important to know. Okay? There are some places that there are not this water injection network, or some places they are injecting water during a lot of years, and we can use this one. Okay? What is the piping pressure limitation? Okay? It's not the same injecting some wells in vacuum pressure, some wells in high pressure, so it's not the same. Okay? We have the power already in the well pads, so we need to centralize all the equipment in one area, or we can move some equipment in some area because we have power in the well pads. It's very important. Okay. And I say that 2 seconds. It's very important to know with these 3 parameters we need to know is we move into the modular polymer facilities, or we can go to the centralized polymer facility. So in the next slide we can check that which Argentina project move into the modular and Suriname project will move into the centralized. Why? Because there are a lot of factors. There are water injection network, pipe pressure limitation, and also the condition of the site. You know, this working in the Patagonia desert and working in the jungle in Suriname. So before that, it's very important these 2 points. Okay. And also, that is very important is logistics. How we can deliver my polymer. It's a big problem. I can deliver the polymer on site, but maybe I can move it to an modular. I have the capacity to send this polymer to this side, this modular facility. I need to centralize everything because I cannot move the people, I cannot move the polymer to the web. Okay. The capacity investment. So the company he can stay from 1 month to 25 years. That he can have the money to do that. The OPEX, CAPEX, and project scale. It's time. UR is about time. It's not 1 day, 3 months, no pilot working with time. It's years in order to have the results. Okay, it's very important. So, so in the next slide, we want to present that. We want to present that how we take a decision with the customer to move into modular facilities, and another case like Suriname, we move a centralized facilities.
I don't. Okay, so we're going to introduce you about Greenfield. So Greenfield is owned by YPF. So national private company, YPF. So the field is in south of Argentina, in Comodoro Rivadavia, Golfo San Jorge Basin. So the field has separated Greenfield in 3 zones, so Greenfield Norte 2, Greenfield Norte and Greenfield 2. So they are separated here for some falla and faults. So some reservoir properties of this field. So we are talking consolidated sands, fluvial type, this deformation is called treble. There are 3 main strategic sexes. I'm going to see here. So the first one is very unconsolidated, and the 2 bottom ones are consolidated but fluvial. Temperatures, medium temperature, we are talking about 60 degrees Celsius reservoir temperature. And the quality is very good. So 22%, from 22 to 32% on porosity and permeability. Multi-darcy will go from more than 1 darcy, and you have a straight here in the first formation, more than 20 darcy. And the live oil viscosity is 120 centimeters at reservoir temperature. So this scenario, we have multi-layer formation with heterogeneity and medium condition. Temperature and salinity, as you remember, are important for chemical selection. So, field development. The field was discovered in 2000. The primary production started in 2002, and the secondary production was implemented 10 years later, more or less, starting 2012, 2014, depending on the areas. So, one parameter that you already need to know, the Greenfield will have a high pressure network available. So that will be important for the polymer flooding design and for the strategy that they will follow. So as mentioned, these are good properties for polymer flooding implementation. We have medium low temperature and salinity. Talking later on the salinity, what is 50,000 ppm from NaCl. The multi-layer formation with high heterogeneity and medium oil viscosity. So you can imagine there are a lot of bipiazole that will be here. So first, they decided to go through a polymer injectivity test. So here, the objective was to reduce the risk of the polymer flooding project. We wanted to determine the retention, the polymer. So the inject polymer, how much is really giving this viscosity, how much is not, how much is going to be absorbed in the drug, for example, or mechanically trapped in the reservoir. So these are polymer that is not giving viscosity and helping to reduce the mobility gradient. The duration of this polymer injectivity test were 20 months. So there was a first part of injection and then back production test. So they first injected water for 5 months. They injected polymer for 3 months, and then back produced for 12 months. That allows them to measure the viscosity they have when they back produce. That when they compare was relatively low to the injected solution, and the concentration measurement that were done give them around 35 to 26 micrograms of polymer per gram of rock. So here you have this is the completion of the well used. They isolate one zone. Here you have the inline viscometer. Is a technology that was patented by SNF that allows you to measure inline the viscosity of the fluid. So it can be used for the injection just to assure that you're injecting the good viscosity, or even when it's back produced to assure that was the way it was done in this case, to assure that to check the viscosity of the gap. So they say, okay, we're going to move to the pilots. So they move to one pilot. So it's an area that has been 10 years of primary production, and that has been other flooding since 2012. So the pilot was the design was in spacing of 170, 190 meters. They have 5 spot patterns. 4 injector and 10 producer wells. So 1 central and 9 offsets. So that was quite smart because they allowed them to check the effect of the polymer in a confined area. I mean, this producer well is completely surrounded by polymer injection, and the results of the 9 offset wells that were supported here by injector wells and here by polymer wells. So that was the way for them to check the economics and see if this was feasible for water classification or not. Yeah, go ahead.
What's the criteria for choosing this volume load and putting on that location?
Actually, it was how the field was developed. So the fellow was developed this way, and so I'm not sure they make infill drilling here to make the well. One of the, if they don't have this, imagine that they don't have injector. If they convert, that is another strategy. The producer to injector could be feasible, but the problem is that you will have a high spacing from the injector from the converted injector to the producer. So that will make more time to get a response. So frankly, I'm not sure if this was the original configuration of the well, or they make the infill drilling here. But one of the parameters that you need to know is here it's interesting because you have the confined area that's allowed to further know the economics really in detail, to go to the specification, and then the spacing. So the time to get the response. Good. Good.
Just to make sure all these wells are vertical.
Yeah, vertical wells. Vertical. There are also cases of horizontal wells, but here not. Not I have Venezuela. Not if they are used with heavy oil wells. They are more with horizontal wells. In Canada, the majority of the wells are horizontals. The case of Suriname, they are vertical, but it's heavy oil. So don't take that as an example, but can be polymer technology can be implemented in horizontal wells or vertical wells. In Canada, for example, they have injector producer injector. So they really, I'm gonna confine this area, and the spacing is even lower. But so it's a way to confine the pattern in a way. I mean, for this case was already vertical and they follow this. So for the polymer design, here you see the ionicity on different points, 12,000 ppm. It's lower than seawater chemical composition. It was enough, it was not high enough to go to very more expensive chemistries for polymer selection. The dosage was 2,500 to 3,000 ppm. So here they have the equipment that they were using for this. This was not in a container, as shown Eduardo in the last stage, in the previous part.
Yeah, that was one a little Unity, the little one that we have. So for this kind of project, but because the water injection was no bigger. So and after that we use this Unity like 5 years, and we use now for another project that we can see in another slide, for another project with another 5 years.
So to mention it, we also mature. I mean, from this that was one of our first projects in South America to where we are now. So then we really, for logistics terms, it's much easier to put everything in a container, 40 feet container, and ship everything by boat. That
was locally here.
It was built locally in Argentina. So well, here you have how the big bag, the polymer in powder is supplied in big bags, 750 kilograms. Then it is transferred to a hopper silo, and then here you have the silo, and later you have the material. You have more specific photos. So then we move to the polymer results. So in the central pattern, they got 11% of original in place above water flying, and the offset well more than 6% above water flying. Also, that's something that was interesting is the water cut reduction. So as they start mobilizing some oil and blocking in some case the high permeability high permeability channels. So there were no more water that was produced. So they start reducing this water cut in the production. They got some injectivity loss, but thanks to the H pump that were available, they allowed to continue with the flow rate, and they never go above the parting pressure. So something that was also a key parameter was the good quality of the water during the whole pilot, in terms of boiling water, total suspension, total solid suspension, etc. So that's allowed a good viscosity, average good viscosity during the whole project, to keep the same mobility ratio in the whole time and a good injectivity. And here you have the decrease of the water cut by per volume inject. Here we go. So here they decide we go ahead with the modification, and Eduardo will explain the strategy that they follow to do that.
So we finished the PID test, and we move into the pilot test that was 8 years. Okay, that we did for 7 years in this area. And YPF take the decision that that's working good, we have good results, we move into full kit case. Okay, and remember that I said that we have modular case and we have sequence case. Why we move into the modular case? We have this limit is in Patagonia desert, and there are the facility to move and to start the equipment in different areas. Also, YPF want to use this one unity to move it in 2 years, 3 years to another wetlands. Okay, so we say, okay, I don't want to create a facility center. I want to move this unity to another one. So in this moment, we have 25. We have 15 unities in this moment working in this area, and the idea is in 2 years to move each one for another house. Okay? And the idea is only in the next year have 10 unities more in another areas in order to start to inject in point. So what is the important about the model full sheet development is that we can store in the wetland, near the wetland. I mean, you don't need to a lot of pipe, injection pipe. You don't need to store another. If you store your centralized unit, you need a lot of pipe to go into each well. We're talking about now in this moment 120 wells, injection wells. Yes. So we cannot put a lot of injection pipe. So we move it near the wells. Okay. We reduce that. Okay. We have what is important that the quick connection. We plug and we pump it. This is the So for that we have we start design our cost and project time step by step because we can the customer can buy some units, check what's going on in this area, and maybe buy another one, and we can flexibility. So we have modern initial capex. Delivery time is very fast. We're talking about 1 year fabrication, 1 month commissioning. So in 50 months, 40 months, we are ready to get one. We optimize the footprint because this is 20, 40, or 25 containers. We store 1 container on the other one. Yeah, so and we don't need civil works. We don't get the base plate. We put the containers and we inject. We're talking about working the civil work 3 months, 4 months. So our capex reduce a lot with this kind of unit. Okay, so another thing that this unity coming with YPF coming that we have 10 pumps by unit, but we can spend more. We perform some change in the design. We can put 3-4 pumps more. Okay. So flexible quick and low cost mobilization and demobilization. We can move mobilization in 1 node. We can disconnect it and move this unit to another work. So this is the case that YPF we agree with YPF. They use modular, and we have in this moment, like I say, 15 units working in this moment. Then for the next 2 years, they are to spend all the full. Okay. So this is the unity. We have the silo containers. We have 80 tons capacity. We have injection wells. We have water fragment. Some filters. We need to filter, and we need to remove some solid oil and waters. You know? And we have all the water, the preparation system. Okay? So I say that we start with 4 wells in the pilot, and we move to more than 80, and we work with 120 wells more. In YPF. And this is only for grading. We have another areas in exploration now, like in the south, in the Ukraine area, we have another route running in this moment. Okay. So we injected 0.54 volume of the oil per year. Okay. And the implementation, that's we can start very quickly that, and the response of the oil is very quick. Okay. That is for that YPF case is good one for EOL for
Yeah, like mind that here what YPF did was, okay, I have selected several sweet spots. We're gonna put there, we have already our network, high pressure network for water flooding. We put our skids, we bypass this network, the wells, we bypass and we inject. And then we get 30.3 or 30% of our volume. We take this unit and we move to another sweet spot. So that's allowed them to really continue and take the maximum of that of each spot. So these were the results. So let's continue with the graph that we show later. So they get more than 80% incremental oil, and they save 1.2 million barrels of water due to the water cut reduction. And the utility factor that is how much are going to cost this extra barrel produced. That was 1.76 kilogram of polymer allows them to get 1 barrel of extra oil. And they consider $2.5 kilo for the polymer, you get your math. Depending on the cost of the barrel, I think you make your economy. How is the way forward? That is following YPF. So to remember the pilot of the 4 wells, okay, was now that they have already made the polymer flooding, and they are reached something to the SOR to reduce oil saturation. Say, okay, we're gonna add surfactant to the chemical cocktail. So that is allowed to remove a little bit more this residual oil, this oil that is in the reservoir. So for that, they have made some tests in the lab to check the good surfactant and the good salinity that is required to reach to reduce the false tension. This is the cocktail that they have. So this is the photo of the pilot. So they have done 3 months of cell injection, and they should be getting the compound this year. So this is another strategy. Some companies go directly to the surfactant polymer slug, and they push this slug with polymer. Here has been the other way around. They go through polymer flooding, so that's allowed them to get some time to better select the surfactant cocktail that normally require more time in terms of development. So during the implementation of the polymer flooding, they get some time. They get a good formulation, and then when they arrive to the residual saturation, they implement the surfactant polymer. So now we go something completely different. Suriname case and by radio field. So every time they have C presentation of the Soxoli team, they always start saying where is Suriname. So maybe here in Brazil, it's not that much difficult, but when they're in Europe, Suriname, they don't know very well where to place it. So what you can see here above Brazil, so Soxoli is the national company there. Now it's a little bit more common because of the offshore asset that they have discovered recently. But well, the daily production is around 7,000 barrels per day. This is the Tamarayo field next to Calcutta in the onshore side, in the north part of the country. Country that is 90% of the country is jungle. The only country that speak Netherlands, apart from Holland. So quite curious country. So now talking about the reservoir. These are the reservoir properties of Tamarayo field. So we have 2 areas, T1 and T2 sands, both unconsolidated. T1 is the main one, fluvial shallow marine system, very heterogeneous as well. 525 25 million barrels originally in place, very shallow, so very low temperature, very good reservoir quality. So very high porosity, very high permeability. And we're talking about a heavy oil, much heavier than in the case. We're talking about 650 and 1100 centipoise at reservoir condition. So this is the field, over 1,000 field, over 1,000 wells per drill, gravel pack completion, very good primary recovery, very, very good. There's no network water because, well, very good properties for polymer flooding, low temperature, low salinity. They are use Salamanca River water for water flooding for the polymer flooding implementation. No, they go for primary, tertiary, no secondary at all. So the water salinity is like almost fresh water, right?
It's fresh water.
It's fresh water, so we're talking about 100 ppm, maybe. So they don't need that much concentration to get high values of high viscosity. They're injecting 300 ppm of polyacrylamide or 350 ppm of polyacrylamide, the standard one.
Probably difference between Greenvik, because Greenvik injecting 5,000 ppm.
The pilot was 2,500. Here is 350.
So here is water river, and Greenvik in Argentina is water pollution. So you can see the difference between
how the salinity is important. The temperature is gonna decide, give us more which chemistry we're gonna use. The salinity is more the amount of polymer that we need to reach the target of the viscosity. So, I mean, then sometimes they need to decide. I mean, we drill another well, or we make a test of the technology. Hopefully, very good. They tried the polymer injection, okay? But I mean, for them to drill a new well is not very expensive at all. So, well, this project started in September 2008 with 3 wells, vertical as well. So they have 9 offshore offset producer in same pattern configuration as Greenvik, and they have 23 indirect offshore offset producer wells. So this was what they has planned. So 200 barrels and 800 psi at 40 centipoise, and finally they increase a little bit more the flow rate, and they make different trials of the different viscosities. Here are the results of the pilots. So we have here the barrel oil production. Here we start the first well, second well, and third well. And here we see the incremental that they get. This is the baseline that they have production. And here they have this different increment. Yeah, first viscosity increase, and second viscosity increase from 45 to 85, and from the 85 to 125. Here we have the water cuts that continue increase, but maybe not at the same speed. The thing is, something that they realized here is that they didn't need to go to very high viscosities. It's 45, the increase from double the viscosity injected, they are not getting double of oil. So they decided to go to the expansion with 25 centipoise. And these are the results. I mean, the pilot results were promising, so the incremental oil was modified. This other pattern, they get 10, 6, 20%, depending on the geology that they have in each pattern. It's a little bit complex. Economically was feasible and the challenge were understood. So the expansion, similar area, so there are not that much challenge, and the expected incremental to recovery was 6 to 12%. So they have an expansion strategy with the same scenario than the pilot at different phases, putting in place different injectors.
So this is
How
the
we
same,
do that?
yeah. So this is the same like breathing. We were the pilots, PIT pilots, expansion. And for this project, what is the challenge for this project? The area is jungle. Is a lot of water in the rainy season. You cannot move it. You cannot go to site. You cannot go. You have several animals. You have snakes. You have crocodiles. I just said crocodiles.
Really?
Yeah, a lot.
Okay.
Really, yeah. So the guy, the operation guy, he cannot go to site, and also you have 100 words to check. So we take the decision, say, okay, we need to centralize everything in one area, yeah, and send that all the polymer fluid sent to each well, 100. How we can do that? So we take the decision to move everything in one area. Yeah, centralize all the polymer solution preparation, final solution, and send to the well pads. Okay, so we are single investment. The customer is only one payment. Not like the linear scheme that you send it and like work here you send one linear scheme and the customer buy that. But this is only one. Okay. At this one, what is the matrix is optimize the footprint, synthesize preparation, and design base. So for this one, your civil works is the type of that. It's not like I have a one unity and container, I send that. This is the type of that. Okay. It's the difference between modularized and centralized footprint. The type of that you need. The footprint is bigger. Okay, it's like the unit is not the same. Okay. So the thing is that I said that 2 seconds ago, that is how we can send the flow to the east well, and east well head have different pressure. You have 90 wells, all the wells have not the same pressure. So let's say I do have 5,000 barrels, and I have a vacuum well, and I have another well with pressure. All this production going to the vacuum well. So how can I avoid that? I can control the flow rate for each well. So we know that we cannot shock the valve. We cannot close one valve at the pressure in order to have the buffer in this vacuum wells and the injection and the other pressure wells. So we know that we're talking about the chemical degradation with the H2S and iron plus 2 with oxygen. And we know that the other kind of degradation is mechanical degradation. If we control it, we use the shock valve, we can degrade the polymer. It's mechanical degradation. We know that when we have in final solution polymer like 5,000 ppm, 5,000 ppm, 2,000 ppm, and we shock that, we can reduce the viscosity inside the polymer. That we have mechanical degradation. For that, we open with full open valve, for example. We cannot shock it. So, so for that, we create one system, this LPR system. So we can adjust it for each well. We can install one device like that, and several coils. Each coil that and different leg, and this different leg give me some pressure drops. Okay. So I have one well that 40 bar, another one will have 50 bar. The other one, I cannot use that in order that the good flow rate goes to this well. Okay? So I can adjust my pressure. I can create pressure drop. I can have here 50 bar, but here I have a vacuum in the end of the well, of the coil. So my well can have a vacuum here, but I have 50 well vacuum, but I inject the good flow rate. So we use that in Suriname. We have 19 LPR system installed in each well. Automatically, so we can monitor in a distance, and the operator no need to go to try to achieve what we are doing. So these are our facilities. This is the header with the final solution polymer at 2000 ppm going to the collector, general collector for each well path, and this one going to the LPR system, and this one going to the injection well.
Just to give you a little, to explain a little bit more what's mechanical degradation, you need to imagine the polymer as a long polymer chain, okay? When you may have a high pressure drop that can be done with a standard choke, you're gonna cut this chain in the smaller ones. And when you cut and you get a smaller chain, you're gonna decrease your molecular weight. So that means that the viscosity that you have related to this is gonna be lower. So with what we discover with the VR systems, you make, instead of one single pressure drop, you have different pressure drop, smaller. There is not that much degradation. There is some, but not that much. So the conclusion. So we have presented two different case scenarios where polymer flooding has been implemented with success to revitalize natural assets. So we have different reservoir properties, but optimal conditions for polymer flooding implementation. Low salinity and temperature, and higher viscosity, case of Tambarejo, and medium salinity and temperature, medium heavy oil, and heterogeneous multi-layer, this is really the case. And then for the engineering side, that has well explained Eduardo, different approach from both to the pilot to the full implementation, depending on the challenge that each country, each operator has. So centralized facility, low shear bar, well, Tambarejo field, and mobile airfield development. So this is all that we have for you today. Thank you very much. A pleasure to wrap the questions.
¿Alguien tiene una pregunta?
Nice presentation, Eduardo. Well, I really like your examples about polymer injection. But would you like something more about for cases in offshore fields? You know, I imagine that logistics is more complex than onshore. Could you explain a little bit more
about engineering side? Yes, it's not about also logistics. It's about also the installation of the equipment. You have the space is not the same. The safety is not the same because it's ATEX. And we need to play with that. We need to install little equipment with big capacity to put inside the platform. So we have the case of Equinor powder with emulsion.
Here, it's another challenge. I mean, logistics and transportation is complex in offshore fields. So it's not the same to ship powder from the shore, the offshore platform, or to ship an emulsion. So emulsion allows you to transfer easier from the water supply to the platform compared to powder. Then, depending on the climate that you have, the humidity, etc., can be different. Can be challenging working with
And the storage also.
And the storage.
Big capacity to store polymer powder.
Here in offshore assets, the thing is how the active content you have. Okay, in onshore with powder, you are ready to get 90% of active content. I mean, 90% of the powder that is really giving you viscosity. For emulsion, we're talking about 50% active content. So that means to reach the same concentration, you will need more or less double of material. So that's why offshore is also more complex. So
And the challenge for a pilot detail and full field is so complicated to implement that.
Offshore, as you can imagine, the spacing is much longer. And we're talking about 400, 700 meter spacing from injector to producer. So that means more time to have a response. So I mean, it's complex for a company to really go through, I mean, to make this decision. We have examples. I mean, here in Brazil, we have one. We have a project that's has been injected, has been paused, and is going to be resumed this year. I mean, January next year, going to be resumed. So, and the result that they have gotten, even just with small injection, has been spectacular, mainly in water cut reduction.
Also, we have another project, we're working with another project, but this case is with coil powder. Data. That is, yeah. It's a challenge because we need to storage 220 meters cubic. It's a lot. And we now need to inject it 2 wells, 70,000 barrels per day. It's another challenge, and it's also become onshore and
offshore is much more complex. For low, we have much lower project, low number of project offshore conditions than in offshore conditions. That's for sure. Just because it's much complex, investment is higher, and this is another issue. That is feasible. I mean, here in Peregrino they have very high permeability channel, and they injecting polymer, they block this channel, and they see that directly in water reduction. So, and just making this economy and just reducing the water that they need to handle in production is already a cost that is reduced. Because not only how much oil you're going to get at the end of the day is important, but also what the reduction of the water that you need to treat. So this is also an important challenge in our condition.
So do you have experience with polymer injection producers like injector wells?
Yeah, in Canada, I mean,
like just doing like a bottle of polymer solution, and then you put the well to produce back, and then.
Normally, you need to create a front. So when you say we have the producer has been switched to injector just to start the injection. But once you start injecting, you continue with the injector. You don't put it back in. You're not going to make it go back. The idea is to really to create a front and sweep the reservoir as much as you can as an injector. So the injector to produce solid. And there is no, it's not. There is experience in a single well chemical tracer test. It's more calculated the concentration. So you inject your cocktail, the surfactant, and you see how it works, and then you measure the saturation, then you put the cocktail, and then you put it back, and measure again, and you get the reaction and the saturation like that. Normally, you are not going to go back after that. Here, you might be able to pass for really an objective. Let's now your colleague was.
Thank you for the presentation. It was very nice. I have a question about first, this technology that you're going to use is a kind of thing that you're going to use these days. I mean, when the price of the oil is kind of high, you can implement this, and when the price of the oil is going down, so you're shutting down. So the price of using this technology, using polymer injection in different ways, is outweighs the price that you are going to extract the oil, and is this beneficial if you reduce the oil price reduction, or it's in when everything is okay, you can use this. And let me ask another question. So, and then, as you said, when you're going to have increase the recovery factor, you will have more production of water as well, actually. So how do you treat that? Because environmental, policy in different countries is different, and you cannot easily produce the water, and then the water is kind of problem for you to even to reinject them. So, is it any study that's, for example, you are going to optimize the how can I say recovery factor without considering the recovery factor, the production of water? So,
There is, for your one question, if your question is, are we getting more projects when there are high
No.
prices, when the price of oil is higher? The response is yes, yeah, for sure. And the price of the oil is higher, the economic or the projects are economical, are much more economical, in any case. So
is there any study that you can consider that, for example, for 1 barrel that you are going to increase the recovery factor, how much for example, a company owner should pay?
So here, for example, in the Olympic case was $1.76 for extra barrel produced. Of course. So that is major economics. And then for your second question about the environment, and we also getting when the price of oil is higher, we get more query, but also it's an environmental question because we are getting. This technology allows to increase the life of your assets. So normally that's happening in commodity innovation. So they were getting 30% of recovery oil, and they are getting 12 years more of development of this field thanks to polymer flooding technology. So that's allowed to increase the life of the asset. And then about the question of the water flooding, for example, then the water also production is reduced, so that's beneficial also for the environment. And there was one study. Just talking about for Pellegrino. Actually, they request what happened. Equinox request. But for Norway, in Norway, they say what happened.
Yeah, but in Libya, the water cut was 96%, and we reduced to 68, 9%. So when you implement foreign irrigation, you reduce the water production.
I don't know if your question was related to extensive problem environmentally. How was that?
About that. Yes. So when we give them polymer, we reduce the water cut. And when you reduce the water cut, you have no water to inject it. But that's very important the question about the economics of the data about the EOL work is that in this, and we see that in one presentation, we say that in this moment with this change climate about climate change, the countries ask and the people ask to lower resources. And we say also about less and less exploration. Now in Colombia in this moment, the president of Colombia is saying no more exploration. We need to think about EOL. But we need to say that we need oil. So less people, less exploration,
Less investment in
less exploration, and more oil. So that is EOL. So this is now the politics. And you said that 2 seconds ago, that's Libya. Libya was, we move into EOL, no more exploration. We have this area, this is full field area, we have much Maduro campo. Natural side. We need to move this oil. And EOL is the
might be the strategy is oil fracturing, helping this natural assets in this time. Because they know that the water flooding works. They have multi-layer regimes, medium oil viscosity, it works well. So the idea is to continue implementing that and increase the life of the oil.
Okay. Nowadays, what is the average price of 1 kilogram of synthetic oil?
2.5. 2.5 USD per kilo. So I mean, it's an investment. They get a recovery. So
Another question. The utility factor that you showed in the presentation is 1.76.
yeah,
This value was constant for how many years, or it was constant for
that was at the end of the pilot, if I'm not wrong. So 8 years we made the pilot, right?
The pilot is like 8 years, 7 years.
So at the end of the pitch, at the end of the page, they make this pilot. For sure. I mean, for a company, the pilot is not is to try the goal is to try the technology. To try technology to see the economics that you have behind. And then in the massification, they are making money to reduce costs. That was okay.
Yes, we have a question here that Eduardo Ramirez dos Santos faced on YouTube. The question is, what was the field where you have the highest oil viscosity, and how was the injection strategy that you made to do the project?
I would say Canada and Venezuela. I want to talk about Venezuela because it's the one that I'm more experienced and I have been more closely. In Venezuela, they were talking about it was 3,000 oil viscosity, or 3,000 oil viscosity. And they go through horizontal wells, and they didn't make any water flooding. There was a competition between steam flooding and polymer flooding. The issue was that the thickness of the reservoir was so thick, you are gonna hit losses in the steam. So what was much more interesting to inject polymer. So they go through horizontal wells deployment. So inject horizontal, so injector producer, all in the horizontal way, and they reduce with low water injection. Very low. It was 200 or 500 barrels per day.
We start at 700 barrels per day.
They started at more 2,000 and they go to 700.
Here, the second question that he did was how was the incremental recovery that you have here?
Well, we got very good results, but unfortunately, due to the political situation in the country, we didn't go that much longer. But well, you have Pelican Lake, you have more than 10% of our recovery factor. Pelican Lake is a good example of heavy oil assets. For sure, if you go to, you have project with 1,070 plus oil and 10,000 deploys oil. It's going to work better in 1,000 than in 10,000. It works good, but it won't work in the oil.
Okay. So, the last week, I hear some topic that was interesting for me. That was mixing one biopolymer with adapan, one HPAN. Yes. I want to know how is the synergy that have the two polymers to have to do that experiment. If it's possible, it's better combine. I don't know if it's better to combine both or it's something that people try to do.
I only know one company that has done that in the world. It's in Argentina. It's called Capsa. They want to make a synergy between Santangon, it's a biopolymer, and HPAN.
Yes.
So they consider that Santangon is more rigid chain, long chain, and the HPAN is more flexible. So they have done some study. They consider they have some synergy and that work well. The problem with Santander is that it's going to be dependent on the other markets, as food industry market. So the price can vary a lot.
Okay.
In HPAN, it's a synthetic polymer, it's much more industrialized, so it's normally the tendency is much more low, so there's not that much variation in price. It's not something that has been really worldwide responding. The fact of combining biopolymer and synthetic polymer. And in terms of really implementation, I have only one project in head where they are using biopolymer.
Okay.
In really pilot phase.
Is there another question for you?
Could you go to the last slide of the last presentation? But for the second part, it's about
the first part or this one? Second part?
Second part.
This one?
No. Yeah. About Argentina. And can you go back, please?
Argentina. Okay,
Yeah. Again. Yeah, this one. This one.
This one.
Last one. Yeah, thank you. It's just to know when you add new products, for example, surfactant in your polymer, you have problems maybe in your pump, something like that. How do you lead with the injection if you need to put other chemical products?
Because we cannot start this project. We're going to start this project, but we have PCP pumps in the production works, and we have some tests that YPF that perform some tests about this topic, and he say nothing about we have the problem with that.
Maybe on the injection side and the production side.
Yeah, in the injection side.
Injection side.
Yeah, if there is
in
a problem.
Process, the only thing that's going to change. Here, okay, so you have your mild solution, you mix with water, you have the static mixer. So here you have your diluted solution at the target viscosity that you want. You're going to have another entry of the surfactant and another static mixer to really get a good homogenize the bulk solution. And then the viscosity can change, the final viscosity, because you have the viscosity that you can get with the surfactant plus the polymer. But normally we use triplex pumps that are designed to go to high viscosity. So there is, when we are gonna check with our provider, with our HP pumps provider, we put in the limits of the specification of the final viscosity solution. So normally it's considered in the design. I don't know if this is all your question.
Yeah.
Thank you.
Thank you for your presentation, very interesting. Well, I have some questions. The first one, you say that the production costs about 2.5 per
Polymer.
yeah, because of the polymer. But what about the production cost? This is the injection cost and the production
The cost of the polymer itself. When you go to S&M, say, hey, I want a polymer. Okay, it's $2.5 per kilo. Then you need to.
But the polymers that you put in the surface from the production costs are not taken into account. Maybe you are going to reduce the.
I mean, the goal this to the final stage. The idea would be to this back to this water pack produced. It could contain some polymer. Use it to put it again in the start of the process and allows you to reduce the fresh polymer that you're using. So we have made some experiments using water produced with some polymer and getting some viscosity. sorry, I'm explaining that you have first fresh water with polymer. You need 1,000 ppm. You get at the produced water, you get 200 ppm polymer. So if you mix that with fresh water, you don't need to go to 1,000 ppm to get the same viscosity. You only need 500 ppm. So the polymer that is in the produced water could be used to continue polymer flooding. So this is the ideal of idea. There are some challenges when you have polymer that is back produced because you have some viscosity in your installation. So normally the separators and all the design, the process has not been designed for higher viscosities. So there is some challenges that are there and need to be treated. Normally, I mean, in any case, this is not a stopper for the project. Why? Yeah, we have been investing for more than 10 years. They are getting polymer produced increase or separation. That's still doable. The predator to inject in another acid to meet with the fresh polymer and reduce the amount of fresh polymer. That would be the idea.
But you want to know what is the price to take 1 barrel of polymer into the well? No? That's the question. You ask
because to do some kind of studies, it's very important to take into account.
There are a lot of things like that because that's injecting 1 mole of polymer. Also to account the what use that the
Polymer at the beginning, we are thinking facilities in a whole project.
I have another question. Before starting a project with polymers, of course you have to have done some experimental studies and also reservoir simulation study, and then go to the field. I would like to know how far are these results that you got in the field from the results that you got in the simulation results and the experimental study.
Pilot phase that we can see the reaction of the pollution well in 1 month. There are another well that is 6 months. It depends on the rest.
It's also depending how the kind of company you have in front of you. I mean, there is more companies that are more patient, that they're going to take more caution on what they are doing. They're going to do a good modeling, be sure before injecting anything in the reservoir. And there are other companies that who really believe in the technology. They're going to go much quicker in the implementation of the field.
That's important because there are some companies that he not start with the pit, he moving to the pilot phase. Because if the reservoir is to be stronger, and I'm confident that in 4 wells on 5 wells is working good, and it's not moving to the pilot.
So it depends on the system made there.
And also depends on the reservoir because sometimes like Venezuela, the simulation says 6 months. 1 or 6 months, what year? So 2 times because there are some modelization was not good. We observed some fracture in the reservoir that all the polymer going to this fracture and another way.
Modeling is tricky also because it's hard to implement it for polymer. Model shifting behavior, fracture, that can be considered. So it's tricky.
And we need to evaluate every time we need to evaluate the ramp-up. So maybe, okay, this concentration, this program is not working good, I should move it to another, we increase the concentration. Or maybe the polymer was not a good selection, we move it to another polymer.
Yeah, I mean, it will depend on the decision maker, how, I mean, in Argentina, for example, if you have 4 kilometers next to you, you have another operator who is making the technology and it's working well, say, okay, I'm going to do the same. There's not that much to decide. Same formation, same kind of reservoir. The level of formation is very, very high formation. So the other operator can know that it's working there, so it's not going to be that much different.
Yeah, in the presentation you mentioned that because the fact that you inject water for of the polymers so you can reduce the risk, right? But also because the importance of doing all these tests, you should advise on starting as early as possible polymer project.
Yeah, I mean the early. I mean, for example, for heavy oils, if you have, if you go through waterfront, you're going to create this hypermobility. You're going to create this channel injector to the producer. And once this is done, even if you inject polymer and try to create a better product, the polymer is going to go through the channel. So this preferential path is going to be followed physically by the polymer. It is not that dramatic as water. It's going to be hard. So, for example, in Venezuela, in Statsoli, and in other heavy Canada, heavy oil pools, they go from primary to tertiary directly. You can make 1 week or 1 month injection of water just to see that the reservoir can do it. But not for a long time to avoid this challenge.
Thank you. That's all from my side.
Thank you very much.
So with that, I think we can close the conference. We're going to give you some gifts for.
Appreciate it. Thank you very much.
You can show close.
SNF for easy, cost-efficient, and sustainable EOR solutions. In a world where the energy demand continues to climb, oil extraction must be done in an environmentally responsible way. For EOR operations, this means reducing CO2 emissions. When changing from water flood to polymer flood, the water production can be reduced from 9 barrels of water to 3 barrels of water per produced barrel of oil. SNF achieves this with modular plug-and-pump installations for quick and cost-effective unit implementation with many added benefits. Polymer flooding involves increasing the viscosity of injection water to enhance sweep efficiency and ultimate recovery of oil within a deposit. SNF assists clients through every step of the process. From assisting screening and reservoir studies, polymer logistics to on-site storage, mixing, and injection. SNF designs, implements, and operates on-site facilities for the client. polymer flooding has a higher added value than water flooding. Due to the greater sweep efficiency of polymer flooding, the overall recovery will be accelerated with significant water production reduction per barrel of oil. Using SNF system, clients' water cut went from 90% to 70%, which means 3 times less water production per extra produced barrel of oil, savings on lifting operation and production costs. These benefits also result in a reduction of up to 3 times in greenhouse gas emissions during the operations. SNF improves the efficiency of oil production processes. Because polymer flooding is easy to implement and more mature than other methods, development time will be significantly reduced.